So good afternoon. I'm Nicole. I'm the manager of VAC Wellington, as Paula said. I'm going to give you an update on the recent progress in the development of the Quantitative Volcanic Ash Concentration Information Service, otherwise known as QVA. So we've done quite a few of these QVA talks over the years, but if you're new to volcanic ash hazard space, here's a quick recap of the history. So Met Service operates one of 9 volcanic ash advisory centres. We are known as VAC Wellington. Our role is to monitor and respond to reports of volcanic ash in the atmosphere by providing forecasts to the aviation community on ash cloud extent and movement. The ash warnings are currently issued in the form of volcanic ash advisories and a corresponding graphic. These are typically based on discernible ash, which is what a satellite or other remote sensing instrument detects. The lower limit of discernible ash from satellites is approximately 0.1 to 0.2 milligrams per cubic meter. So the 2010 Icelandic eruption altogether now caused large flight disruption across Europe. This led to an industry request for VACs to provide ash concentration information rather than just qualitative information. So Rolls-Royce engines have been investigating the relationship between exposure duration and ash concentration with relation to safe operating levels. They have identified acceptable exposure doses for specific engine types. So QVA information offers operators the opportunity to move away from the traditional discernible ash criteria and instead use certified engine susceptibility for flight planning routes and in-flight replanning. So all VACs use something called an atmospheric dispersion model. These are initialized using information about the release of ash into the atmosphere. So we want to know what volcano is erupting, where is the ash being released, what height into the atmosphere is it being released to, and how much ash is being released. Collectively, we call these eruption source parameters. Our models are also being driven by meteorological data. For example, what way is the wind blowing? So we need to know what the weather forecast is. Both the weather forecast and the eruption source parameters are underpinned by observations. We then run our dispersion models and generate a lot of model output. Again, we compare this model output to current and past observations, namely using satellite imagery, but we also use other sources such as radar, ground reports, and importantly, pilot reports. We then generate the final product for our customers. So traditionally, this comes in the form of a VAA and the corresponding VAG. These indicate the observed or estimated location of a volcanic ash cloud, defined as concentrations greater than 0.2 milligrams per meter cubed, with a +6, +12, and +18 hour forecast in the form of very simple polygons. So over the last decade, there has been significant advances in our scientific and technical capabilities to provide a volcanic ash forecast, and QVA will reflect this. The forecasts will be higher resolution, both temporal and spatial, and offer operators an opportunity to fly more efficient routes. Probabilistic forecasts will also be offered to further help optimize airspace planning. So what is QVA? So QVA is largely a data service, allowing customers to customize to their own requirements. VACs will be required to provide 3 things: ash concentration data sets, IWXM objects, which are just more sophisticated polygons, and also probabilistic data sets. Noting that this is a new service, VACs have also agreed to provide supplementary graphics to help customers with data visualization. The data will have a horizontal resolution of 0.25 degrees with 12 vertical levels between surface to flight level 600. There will also be a higher temporal resolution with 3 hourly time steps and the forecast will go out to 24 hours. Importantly, areas will be broken into 5 concentration thresholds, defined from very low to very high. This means that all VACs will be forecasting how much ash is expected to be in the atmosphere, with greater resolution than the current VAA. And for the first time, we'll be generating probabilistic forecasts and providing the raw data to aviation customers. All right, moving on early. So, a case study. This is to give you an idea of how QVA may be used. This has been kindly provided by VAC London and uses a hypothetical eruption of a known active volcano in Iceland, representing a moderate-sized eruption. So several hours into the hypothetical eruption, on the left here is an example of a traditional VAG. It's 3 simple polygons divided into broad vertical levels, indicating the location of forecast volcanic ash with concentrations greater than 0.2 milligrams per cubic meter. For the same time step on the right is the new QVA forecast, specifically for flight level 150 to 200. You can instantly see that there is more detail on both where the ash is expected, as well as the concentration amounts, with the blue colour representing low concentrations through to purple for the very high concentrations. Now, remember I said that QVA would be provided at 12 different vertical levels. Let's take a look at the scenario by stepping through these different levels of data. So, starting at the bottom level, which is surface to flight level 50, the colour box around the forecasts allows you to compare the new QVA forecast with the traditional VAA, or VAG. Here in the bottom level, we can see the highest concentration of volcanic ash in the vicinity of the volcano, with low concentrations being transported towards the UK. The QVA area is quite a bit smaller than the red polygon depicted on the VAG. Moving up to flight level 50 to 100, we can see that the extent of the medium to very high concentration area has broadened. Moving up again, we can see that the medium to very high ash concentration is now spreading towards the top of Scotland. And at the next level, you can see that the winds are shifting the plume round and the ash is reaching towards Norway. Collectively, these 3 charts compare to the red polygon on the VAG. So from flight level 200, this area would have been covered by the green polygon in the VAG, again with higher concentrations approaching the coast of Norway. This is at flight level 250 to 300, and it's a reasonably similar area. But at the next level up, the extent of the ash cloud is starting to contract. From flight level 350, this area would have been covered by the blue polygon in the VAG, and the area is continuing to contract. At flight level 400 to 450, the ash area is expected to be largely just off the Iceland coast. By the time we get to flight level 450 to 500, the area is smaller again and mostly over Iceland. And by flight level 500 to 550, you can see that we're now predicting very little ash in the atmosphere and only at the low to medium concentrations. And finally, at the top level, we're predicting no areas of volcanic ash with concentrations greater than 0.2 milligrams per meter cubed. So taken as a whole, you can see that you have much clearer 3-dimensional description of how the location, extent, and concentration of ash will vary with height through the atmosphere. So we're also going to be producing data every 3 hourly time steps out to 24 hours, which will be important to understand how the ash cloud areas are forecast to move and change over time. In this example, the green boxes on the left are for flight level 300 to 350. In 6 hours' time, you can see that the ash cloud is expected to start looping up to the north and thin out at its furthest point, where concentrations are less than 2 milligrams per metre cubed. Some operators may have safety plans that allow them to fly through this area. You can also see that the number of supplementary charts is starting to get quite large. With 12 different levels at 3 hourly resolutions, we're starting to look at over 100 charts of information for one run. Here's an example of the IWIXM objects. These are showing you the maximum concentration at possible levels in the atmosphere. So they're helping to refine the information you have just seen. But they are much more sophisticated than the VAG polygons, which have restrictions on the number of points we can use to describe an area. You can see that these also have the predicted concentrations within those polygons too. So the last data set we'll be providing is probabilistic forecasts. The idea is to be able to provide you with a narrative on our confidence we have in our forecasts at a moment in time. There are multiple sources of uncertainty associated with generating these forecasts, notably the uncertainty associated with eruption source parameters. As you can imagine, measuring the height of a VA cloud and defining how much ash is being ejected can be quite tricky. We also know that there can be uncertainties associated with our weather models. The key parameters here are the wind field, because we want to know which way and what speed the wind is blowing at different levels. The other key parameter is precipitation, because this helps to remove ash from the atmosphere. So these charts represent our confidence in the location and concentration of ash at a particular time and level, taking into account the uncertainties from both weather models and the eruption source parameters. In the graphic, the highest confidence areas are represented by darker shades, while lower confidence areas are the lighter shades. So returning to our case study, on the left we had our traditional VAG that was generated for this scenario. In the middle, we have the ash concentration forecast for QVA at flight level 200 to 250. And on the right, we have the probabilistic forecast for the same time and flight level for ash concentrations exceeding 0.2 milligrams per metre cubed. Comparing the two QVA products, you can see that there is largely good agreement, but in the probabilistic chart, it hints that there are a few solutions that spread the ash a bit further to the north. We will be producing these probabilistic data sets, for the same 12 vertical levels and 3 hourly time steps out to 24 hours, for each of the 4 defined concentration thresholds between low and very high. So just very briefly, I also wanted to show you a QV example for the New Zealand area. This scenario took the eruption source parameters from the 1996 Ruapehu eruption while using the weather model for the day of the 8th of January last month. This is just a quick snapshot of the model output for a single time step at 6 of the vertical levels, compared with the example of the VAG. You can easily see that there is far more detail in the QVA product, which can support decision-making by operators. Additionally, here is what the probabilistic data looks like for the different concentration amounts at flight level 300 to 350, noting the closely combined areas indicate high confidence in the forecast. So when will all this happen? There will be a phased transition across the VACs as we move towards QVA, and this is the current suggested timeline. From November 2025, which is this year, VACs in a position to do so will start providing QVA information. And from November 2026, it will be a recommended practice for significant volcanic ash clouds in Annex 3. It is expected to become a standard in 2030. However, please note that VACs will continue to generate the traditional VAA and VAG products during this period. So just to give you a bit of insight into how we can see the forecaster workflow for QVA issuance. So on the left, the initial steps will largely be unchanged. We will continue with monitoring and will react to an eruption or an alert of eruption by issuing our traditional initial VAA. We would trigger our dispersion models and then issue a full VAA. In the initial rollout of QVA, FACTS are only required to issue QVA for significant volcanic ash clouds. What is significant is an interesting question. As VACTS, we are aiming for a consistent global approach while also trying to keep in mind our different customer requirements and different types of and frequencies of eruptions within each area. If we felt the eruption could be considered significant, we would rerun our dispersion models. There would be an element of automation of the IWICs and polygons and VAA, but the forecaster would still be involved in quality control and checking the data is lining up with what we are observing. If the data isn't looking right, they can just choose to stick with the VAA for now. This is just for the early rollout of the service, with the intention of working towards a full operating capability where QVA will be issued for all eruptions. It is worth noting that QVA won't be available immediately after an eruption. It may take the forecaster a little bit of time to get a handle of some of those eruption source parameters we talked about earlier, namely the height of the ash cloud and the duration of the eruption. If you can remember back to the Hungatonga Hunga-Haepi eruption in January 2022, for such a big eruption that went into the stratosphere and beyond, it took the duty forecasters a good couple of hours to analyse and start to understand the height of that event. So finally, I'll just sum up by saying this new service has been a long time in the planning, and it has been a true global collaboration of experts working hard to solve this problem. It's very exciting to see this new service so close to going live. So thanks and happy for questions.